Okay, as we talk more about balancing chemical equations, one thing we want to remember is to determine the number of atoms of an element in an equation, multiply the subscript by the coefficient. And the coefficient counts for every element in the compound. So if we look at this coefficient of 2 in front of water, to count the total number of hydrogen, it's 2 times 2, and then it's also 2 times 1 for the oxygen from these water molecules. And then if we have an element that is in 2 different compounds, then we add the total number. So here's oxygen, we have 2 in carbon dioxide, and we also have 2 from water, so my total number is 4. Now some symbols that will be used, we already looked at G for gas, of course L for liquid, S for solid. AQ stands for aqueous, which comes from the Latin word aqua for water, and that means it's dissolved in water. So these up here are going to be pure substances, and this is going to be a solution, mostly water, but then also the chemical dissolved in it. And for our purposes, we're going to care about the chemical more than we're going to care about water. Now sometimes energy symbols are used above the arrow for decomposition reactions. This little delta, Greek letter delta triangle, stands for heat. H, nu, this is the Greek letter nu, stands for light. Shock means there's some mechanical shaking up of the material, and elect means we're adding electricity. All of these can give a reaction the necessary energy it needs. Okay, now let's look at the steps of writing a balanced chemical equation. Sometimes you'll be given the basic equation, and sometimes you need to write it from words, as we saw in our earlier example. Then we need to count the number of atoms of each element on each side of the equation. And we do that by multiplying the coefficient, which at this point is 1, times the subscript. Sometimes equations are already balanced with the coefficients of 1. If we're looking at a polyatomic ion and it is on both sides of the arrow, then we can just count polyatomic ions instead of breaking them down into the elements that make them up. After we have our equation, we pick an element to balance. And a good element to choose is if there's an element that is found in only one compound on both sides. If an element exists as a free element all by itself somewhere in the equation, then save that one for last. That's going to be easiest to balance after everything else is balanced. Now remember, we're going to balance each element by changing the coefficients in front of the compounds in which that element exists. The coefficients affect all the elements in the formula. And when we change the coefficient, we may unbalance some other elements. So we have to go back and forth until the whole equation is balanced. So let's look at this example. Here's what we're given. When magnesium metal burns in air, it produces a white powdery compound, magnesium oxide. And here's magnesium metal. When it burns, it forms this white smoke, which is this compound here. So the first thing we want to do is write our equation. We know that magnesium is Mg. It's a metal, so it's going to be solid at room temperature. We know that oxygen is O2, and at room temperature it's going to be a gas. Now how do we know what the formula of this is? Well, magnesium is an alkaline earth metal, so therefore it always has a charge of positive 2. Oxygen always has negative 2. So because these have equal and opposite signs, charges, it is a 1-to-1 ratio. Since it's an ionic compound, it's always solid. Now that we have written our basic equation, let's go back and count the number of atoms on each side. 1 magnesium, 1 times 2 is 2 oxygen. So 2 oxygen on the reactant side and only 1 on the product side. Our magnesium is balanced, but our oxygen is not. If only one element is not balanced, then the whole equation is not balanced. So we're going to choose an element to balance. Of course, it's going to be oxygen because it's the only one that's not balanced. And we can balance it by putting a 2 in front of this compound. Then we'll have 2 times 1 oxygen, and our oxygens will be balanced if I put a 2 right there. Now, if I put a 2 right there, what happens is that changes my magnesium. Now my magnesium is also 2. So I've got to go back and balance my magnesium. And that happens a lot. When you go to balance one element, it may unbalance your others. You can go back and balance them. So to balance my magnesium, I've got to put a 2 in front of the magnesium on my reactant side. So now I have 2 times 1, or 2 magnesiums on my reactant side, 2 magnesiums on my product side, and 2 oxygens on my product side, 2 times 1, and 2 oxygens on my reactant. So now I have a balanced equation, but I had to go back and forth to get there. Okay, let's look at another example. Under appropriate conditions at 1000 degrees Celsius, ammonia gas reacts with oxygen to produce gaseous nitrogen monoxide and steam. Okay, how do we write this? Well, first, it might be helpful to write what we can in words. Ammonia gas plus oxygen gas reacts to form, so that's our arrow, nitrogen monoxide gas, and steam is water in the gas form. So you should know that NH3 is ammonia, oxygen is O2, nitrogen monoxide is NO, and steam is H2O gas. So this takes a little bit of time to get from the words to the actual formulas. So next we count our atoms. Here we have nitrogen, 1 on the reactant side, 1 on the product. Let's look at our hydrogen next. 3 on our reactant side, 2 on our product. So we know now it's not balanced. 2 oxygen on my reactant and 2 on my product. So it doesn't matter that these 2 elements are balanced. My hydrogen is not, and I've got to balance that. So I'm going to start with my hydrogen since it's the only one that's not balanced. But if anything else wasn't balanced, I would start with nitrogen, hydrogen, and I would do oxygen last, because oxygen is in 2 different compounds over here, and we're going to save that one for last, always. Okay, so I've got to balance my hydrogen. I have 3 over here, I have 2 over here. What I'm going to look for is the least common denominator between 2 and 3, which is going to be 6. So I want 6 hydrogen on both sides. To do that, I'm going to put a 2 in front of my nitrogen on the reactant side, and I'm going to put a 3 as a coefficient of my hydrogen on the product side. So then I'll have 2 times 3, 2 times 3, it'll give me 6 hydrogens on each side. Now when I do that, it balances my hydrogen, but then it changes everything else. So because my oxygen is in 2 compounds, I'm going to save it for last, and I'm going to look at my nitrogen. When I put my coefficient of 2 there, that changed my nitrogen to 2, so I now need 2 nitrogen over here. So I'm going to put a 2 as a coefficient in front of my nitrogen. Now when I do that, it is also going to change my oxygen. This is going to become 2. So now I have a balanced nitrogen. My hydrogen is balanced. The only thing that is not balanced is my oxygen. I have a total of 5 oxygens now on my product side. So here's the equation so far. Everything's balanced except oxygen. Okay, now how do I get 5 over here? What times 2 gives me 5? Well, the answer is 2.5. 2.5 times 2 is 5. Now, that's not where we want to end up, but it's a good starting point. We don't want any fractions or decimals as our coefficients if we're talking about molecules, because we can't have a half of a molecule. How do I get this value to be a whole number? Well, I'm going to multiply by 2. But not only am I going to multiply this by 2, I'm going to multiply every other coefficient by 2. So when I do that, my 2 goes to 4, my 2.5 goes to 5, my 2 goes to 4, and my 3 goes to 6. As long as I multiply every coefficient that I've already written by 2, my equation is still balanced, and let's check. 4 nitrogens on my reactant side, 4 times 3, 12 hydrogens on my reactant side, 5 times 2, 10 oxygen. On my product side, 4 times 1, 4 nitrogens, hydrogen 6 times 2 is 12, and oxygen 4 times 1, 4, 6 times 1, 6. 4 plus 6 is 10. So it's still balanced, and now my coefficients are all whole numbers.